Right. So hello everybody. You can call me Sven, and for money stuff, I do basically I'm a freelance software consultant. But for fun stuff, I do Rust and a fair bit of that. And yeah, so today I'm going to show you how to use Rust in order to speed up your Python. Also, how to use Python in order to slow down your Rust. I'm serious. Actually, we're gonna look into that. And yeah, let's get started. Now, actually, as far as this conference goes, I'm fairly surprised because there were like 3 Rust talks already, I believe. Like this was fairly surprising because like last year there was nothing, and so I'm quite glad that this is kind of working out for us. Right. So, but I believe that I'm presenting a new method that hasn't been brought up in this conference before, and I believe it's quite simple and quite low on boilerplate. So. Yeah, let's dive just into it. And also, I'm going to assume that you have no knowledge of Rust whatsoever. I believe the other talks kind of assumed that you did. I'm going to explain every little bit of syntax, and in fact, we're going to look into what Rust looks like first, and then we're going to discuss the more interesting concepts. All right, so first of all, I'm going to talk about the motivation. Like, there's different reasons for why you would want to use Rust to begin with, right? There's different reasons. Now, I'm going to look at the current approaches in order to fulfill some of these motivations, and then we're going to see how we can actually fulfill the motivation using Rust, and then let's see what we can take away from this talk. All right, so there might be multiple motivations why you might want to do this. Now, obviously, the first, the most intriguing one and probably the highest impact one is to speed up your program. Right, this is always the primary reason, but you might also want to escape the GIL, right, the GIL. In order to do some proper multi-threading, right, because we all know that in Python you can't do proper multi-threading without kind of running some hoops around places, and also you might want to bind to existing system libraries. For instance, if you have if you're a scientist, right, you want to bind to some existing C++ libraries. This might be a thing that you might want to use Rust for building some kind of the glue code, right? So today we're only gonna explore the speed up your program kind of thing, because I also got the vibe from the conference that this is probably the most important topic for everybody. Because Python is kind of slow, right, and we want to make it kind of fast. And now the question is, how do we get there? All right, but let's see how we can which ways currently exist in order to speed up our Python. And as far as that is concerned, we know very well about the C extensions, of course. This is probably the best documented way, but to be honest, they're quite annoying, right? That you have to write lots of boilerplate code. It's not very nice, right? Then there's C types, which is kind of the newer way to do that, but it's kind of discouraged nowadays. And then there's CFFI, which is probably the newest way to do that, but it's also kind of boilerplate heavy, and I don't like that. So there's binding generators like Boost Python, which if it works, it's fine, right? But if it doesn't work, you get megabytes of template messages in C++, which is not very nice. And you have Swig, which also generates Python bindings. Then there's specialized libs which you can use, like Pillow for image manipulation, for instance, or NumPy, which I'm sure many are familiar with, which you can also use to vectorize your code. And if you can fit it into that, it's great, and you should probably just kind of keep it that. But sometimes you just can't, and you have to be, a bit more ingenious about that. And then, of course, there's PyPy, which we all know and love, which is a JIT-based approach to speeding up the program. And in best case, of course, you don't have to do anything, which is also great. And then there's Python, which is a Python dialect, of course. And then there is another binding generator on the block. It's Pyro3, and this is actually what we're going to be using, which is a Rust-based Python kind of binding generator. All right, let's look at why we would actually want to approach in this thing from a new perspective, right? So, why do we even care? So current approaches, at least the manual ones, are unsafe, and by unsafe I mean that you might run into data concurrency issues, you will run into race conditions, dirty reads, dirty writes, stuff like that, right? If you have multiple threads writing the same variable, what you're gonna do. So you're gonna have to handle that. You don't, especially in C, right? You're gonna have to use your own memory management, which is not very nice, and you might run into segmentation faults or uninitialized memory, stuff like that. So we don't like that, right? Now C is not very ergonomic either, right? It's showing its age, right? It doesn't have very nice syntax for solving some concepts. It doesn't have nice lambda syntax. You can kind of do it right, but it's not really nice. Then you have GObject, which is also not very nice. So, right, it's not very nice. So, and then if you use PyPy, right, using a JIT-based approach, it's kind of unreliable, right? You might It might work, it might not work. Doesn't play so nice with C types either, so not really great either. Multithreading, as I just said, like C in multithreading is not the greatest, of words right now. You can do it, but to be honest, like this would probably not be your best choice if you were to speed up your program using that. So instead, we're gonna oxidize our snake or your snake essentially. So we're gonna use Python and Rust in order to make an oxidized snake. Get it? It's like a snake, but it's oxidized. Okay. Right. So what is Rust? As I said, I'm going to assume that you have no idea about Rust, and this is totally fine because it's a Python conference, right? So Rust is safe. You're not going to get any problems with like data races. You're not going to get any initialized memory. Basically, it's very hard for you to crash your program, to be quite honest, right? You can make it unsafe, but you have to be very explicit about it. And the compiler is actually a bit of a bitch about it, to be honest. Like you're gonna spend a lot of time fighting the compiler, but in the end, if it does compile, you can be reasonably sure that at least it won't crash, right? I mean, of course, you can still make logic issues, right? But no programming language probably ever is gonna save you from those, right? So, and also it's gonna save you from multithreading problems. And we're going to see this actually later on why that is. So it's also modern. So by that I mean it has, for instance, like Unicode support built in. It's something like even Python didn't have properly in the second iteration. And it has pretty good looking syntax. It has great, amazing tooling, in fact. We are going to look at that a little bit later, but basically you have a tool called Cargo, which is your package manager, and it's also your build system, and it's all that meshed into one thing, and yeah, that works out quite well. Then it's fast. It's really fast. In fact, it's like C-like fast because it compiles down to the same kind of machine code, and it uses LLVM, or the main Rust implementation uses LLVM as its code generation backend, so that you get all the benefits from that. And then it's statically and strongly typed, so that means that if you have a type, you're going to stick to that. You can't have like a dynamic type thing. So that also means that, of course, we can't do funky things like monkey patching a type or monkey patching a variable, stuff like that. These are things that you have to be tricky about, right? But it works, and you can do it in Rust. And then it's immutable by default. Now, in Python, everything is mutable by default, right? You have a variable, you can choose to change it like 20 times, and it will just kind of work. This is a bit of a problem, really. Like, if you think about it, basically, is most of your data write-heavy or most of your data read-heavy? If you think about it, it's probably read-heavy, right? So it makes sense if most of your data was immutable by default, right? And this will give you some guarantees. And imagine that in Python, you had a compiler which enforces this kind of behavior. And in Rust, you're going to have to be explicit about making things mutable if you want to change them, and then basically just the default is going to be that it's immutable. And actually the compiler is going to warn you. In fact, it's going to crash about that. So, and it's also private by default. That is, in Python, everything is basically importable from everywhere. I know there are some trade tricks which you can do, but essentially everything is always public. So in Rust, everything is always private, which means you're going to have to be explicit about which things you actually export, which data structures you actually export, which functions you export. And this is quite cool because this way, like, you can't export too much, right? It's always better, I believe, to export too little than to export too much, right? And then, as I said, the tooling is amazing, the community is amazing, and I think probably the greatest point is that we have an amazing mascot. Look at that. He's called Ferris, and he is really quite cute. And then, of course, you have a fearless concurrency, so watch out for that. So what does it look like, right? So here we have a Rust program, quite a trivial one. And essentially what you have in the top there, you declare a function using fn as opposed to Python's def. And then you put in an x, and it's a string type. Ignore the ampersand for now, basically as a reference, so that we don't copy the string. We're very explicit about this. And we have a print ln thing. Also ignore the bang there, it's a macro, but just ignore it for now. But essentially, as you see, it looks kind of like the Python equivalent, which is like this, right? And you can see that it's really quite similar, right? One thing to note is that you have the let names as opposed to just names. Basically, you have to be explicit about declaring variables as opposed to changing them. So you have to have the let there, right? But everything else looks kind of the same, right? The iteration looks kind of the same. The printing looks kind of the same. So it's not really all that alien to Python developers, right? There's obviously some funky syntax sometimes that you can build, right? And also it's braced. as opposed to indentation syntax based, which is nice because finally you can make, you can actually format code in an idiomatic fashion and everybody can agree to that. Like, in Python you have people like tab spaces, right, stuff like that. So I think we kind of agreed on 4 spaces, but I know there's some companies which think otherwise, but all right, so that's our our base, what we're gonna build off from. And so Rust and Python. Now I think everybody's waiting for how to actually make Rust and Python work together. So as I said, we're gonna use Py-3, and it allows us to write Python modules in Rust, and allows us to use Python from Rust. So we can do it like both ways. We can make like a Python module, like you would normally make like a module in C and then import it in Python. But you can also have like the interpreter acquire the the GIL, the global interpreter log, and then run the entire Python interpreter in Rust. Not sure why you would do that, but you can do that, right? So let's make a Python module in Rust. So there's a few things to note here. It's gonna look a bit funky at first, but bear with me. So let's just ignore the feature on top there. And then the extern crate is basically like this way you tell the code, the library, to use an external so-called crate. Now a crate is like a package, right? A Python package. Basically just this way you open a package, right? An external package. And then the use is basically like, in Python would look like from something imports asterisk, right? And this is essentially the same. Now I know that we don't like asterisk imports, but bear with me. It's a talk, right? So and then you have this funky-looking PyMod init. Essentially, this tells us what the module itself is going to look like, right? Because in Python you have modules, and in Rust we also kind of do, but you have to like make the bridge explicit, I believe. So this is how that looks like. And then you have a function. You explicitly declare this function using this attribute on top there, the pyfn, and then we call it hello. This is going to be the string that's going to be put into the generated code. And then conveniently it's also the same, the Rust function name is the same as the symbol that we actually export. And then all we do is we just have like this, we take in the name, is a string type, and then we just print the name, and then we have those weirdly looking OKs, which are basically just empty results. Now I'm not going to tell you about Rust and error management. This would be a bit too much, I believe, but basically just say, let's just suppose that in Rust we always have to be explicit about whether we are returning an error or a result, and in this case we are returning results. Right? So let's call this from Python. This is just what it's going to look like. So like any normal Python module, and you're going to see that this is going to be the output, and this actually works. You can actually take it like this. There's no other boilerplate. This just works like that, right? Of course, you're going to have your cargo setup, and this is not much, right? This is just like basically like your default setup that you get if you have like cargo in it, and then off you go. This is all you have to do. There's no CFI shit involved. There's nothing else, right? This just works like that. So I think this is quite amazing. And you can also see that we have some fancy Unicode stuff in the code that also works. All right, so let's build classes. Now Python is famously called an object-oriented language for good reason, and that means we should probably be able to construct classes also from our Rust code. Now Rust doesn't have classes, but Rust has structs. Now structs are kind of like just data structures, which can have other data structures inside of them or other data types. And so think of them like a Python class, but with some fewer bells and whistles. Now we can also bind methods to our structs. And in fact, this is what we do here. We're using the impl statement that you see there. You basically tell it, okay, starting from this point forward, we are implementing this class. So we are giving it functions, right? So you can see here that our class, or our struct, has a list of strings, like the vec string is basically like list of strings. It's just a vector, and the vector maps to Python's list type. Vector is just the same, has the same properties as the Python list. It essentially does. It can grow dynamically. It has one type. In this case, just because Python is dynamic, obviously we kind of have to bow to Rust, basically because we can't have like two different sets of things in there. All right, so and then we have a constructor. Now in Python, the constructor is called init. In this case, we can't have init just because basically at the time that we constructed an object in there, basically because our Rust code owns the, while the Rust code owns the pointers, the Python owns the memory. So we kind of have to work around that by giving making a constructor using new, and then instead of using init like Python uses init. This is kind of weird, but bear with me for a second. But anyway, what we want to show is that we can make a struct that is going to be translated to a Python class that we can construct in Python, and then it's going to have this dynamic list of strings in there, which is our num strings, and we're just going to give back the length of that, right? So let's do this in Python. This is just a tiny little bit of boilerplate, basically, because it can't know which class we're going to add the module to. Which module we're going to add the class to. And then, yeah, this is our little struct there. And then we can just import this struct module that we have, and then from that import the class that we've made, construct the class as you would in normal Python, have the strings in there, and then print the strings, and it's going to say that there's 4 strings in there. It's just fine. All right, so let's do something more interesting, right? Let's calculate pi, but let's use a really bad way to do it, which is essentially, think about it using like Monte Carlo. If you're not familiar, basically, imagine you have like a dart board, right? But you have only like 1/4 of a dartboard, right? And you're throwing darts at it, but you're extremely bad at it, right? So you hit a random position every time you throw a dart, right? And basically what you do is, and just like after you've thrown the darts, you count like which ones are outside, which ones are inside, and then using that you estimate pi. It's an extremely, incorrect way to approximate pi, but it will eventually converge to a correct thing, but it's very bad, but it does fit on the slide, so I chose to go with this. So this is why we have this. So encircle is essentially this method which checks whether the dart that you throw at is inside of this quarter of a circle or not, right? And then we have a function called calc, which basically just runs a number of iterations, and it throws many, many darts. In this case, we throw 1 billion darts at it, and in the end, we just calculate pi using like 4 times the hits divided by the number of iterations and as a float, and this way we get pi. And we just let us run this, and we're gonna end up with a really bad approximation. Like, this is 1 billion runs of this, right? And we have like 3.1416, right? This doesn't quite work. Don't do this, please, ever at home. But we take 4 minutes and 10 seconds to do this, right? This is quite bad, right? We need to go faster, right? Let's make it faster. So we use some Rust code to do this, and essentially, this is a more or less direct translation of that. There's one new construct which we have here, which is this one ... iteration thing that we have. Basically, this is a range. Like in Python, you have ranges using like range, 1, like iterations. This is essentially the same thing, but using Rust syntax. And then on every iteration, we map, like same as in Python. And as we don't care about the value, like the value would be like 1, 2, 3, like we don't care about that. We just want to do something for every iteration that we have. Right? We could do this in a less functional way, but there's a good reason we do this, and we're going to see this in just a little bit. But anyway, so we call our random number generator for every one of these iterations that we have, and it's either going to be a 1 if it's in the circle, or it's a 0 if it's not going to be. And then at the end, we use the sum in order to sum up all of our hits. And then just the same, we just do the same calculation essentially as we did in Python, and this way we're going to get pi. And this is what the binding looks like. It's essentially exactly the same that we had before. And we're just going to run this, like import this, run it, and we're down to 5 seconds, right? But still not feeling it. We need to go even faster, right? So what we're going to do is we're going to parallelize this, and we're going to use a library called Rayon. Now, Rayon is a thing that essentially gives you iterators, but it parallelizes them. So Rust does many things with iterators, because iterators are fairly safe, right? They know their ranges, they can check themselves. So it's pretty cool. So if you look at this code, you will notice that there's very few changes. In fact, there's only 2 lines which have changed, which is this into par iter, so a parallel iterator, which is a thing provided by Rayon. And then instead of map, we have map width. Now, map width is required because you can see that there's this RNG maker, right? We have to be careful, we have to be mindful of our RNG, our random number generator, because we obviously don't want every thread to share the same random number generator state, right? They need to have different states. So I have this RNG maker, which is like which we just import, and it essentially just makes sure that we have a very fast but also well-seeded RNG at our disposal, right? So, and this is exactly the same code, just as the kind of module code. And so we want to run this. And we can see we're down to 1.7 seconds, which is pretty good. Now, this Rayon thing spawned like 8 threads for us, because my laptop has 8 cores, but it will automatically choose the right amount of threads for your machine, and it will also do this in a very efficient manner. So it will prefetch tasks, it will figure out how many tasks there are, and it's going to build its own worker stealing queues, and it's just going to implement this by itself. And that's pretty cool, and we have to do very little. And in fact, this is entirely safe code. So like, there's no way what we could have data races there, right? There's no way that we could mess this up, which is pretty amazing. I think we did very little work there to speed up our Rust program, and it's basically completely parallel. Now, how do we get even faster from there? There's probably a few ways. Like, it would probably help if you didn't use a completely stupid algorithm to approximate pi. This would be a start, right? But more realistically, if we went down this road and absolutely wanted to use this algorithm, you could probably use some SIMD. So like single instruction, multiple data. You've probably heard about SSE instructions from Intel or MMX or AVX2, which are some instructions you can use to speed this up even more. And it's quite easy with Rust. You can also use iterators as a library which just exposes iterators and allows you to work on like 32 floats in parallel, which is pretty great. And then, of course, you can do cache optimizations, which probably you should do this in this order, because cache optimizations are kind of gnarly to get right. Let's look at some graphs, how we actually did. Oh, this looks good. So you can see that CPython didn't do so well. I did just try out Python just for shits and giggles, essentially, and I'm not a Python expert. I probably did something wrong. I think it's probably the slow Python RNG, is what I'm thinking. So let's ignore this for now. Piper did quite a bit better at 46 seconds, and we can see that Rust single-threaded and multi-threaded far exceed that. Thankfully, right, because otherwise we would be feeling pretty stupid at this point. Right, and we can also do it the other way around, right? If we're feeling that our Python is just a bit too fast, right, we can use our Rust is a bit too fast. We can use Python to slow down the Rust quite a bit, which essentially we do by acquiring the GIL. Right, because obviously we have like Python, like Rust can't cheat, right? Even if it's Python, even if it's Rust can't cheat. So we have to acquire the GIL, which is essentially like a mutex in this way. So only one thing can operate on the GIL mutably. And then we import Python, and then we just kind of import, like using the Python interpreter, we import sys, and then we can just get the version from then. You can see that it actually prints this just fine. And this is actually, this actually run on my system, and this is what it prints. But why would you do this? To be honest, I have no idea. But you can do it if you ever maybe there's actually a reason, right? Maybe if you want to import, if you want to use some kind of odd kind of Python library in your Rust code, I don't know. But there you go. All right. So takeaways, all right? Rust can make your Python quite fast, and the Pio3 integration is really quite easy, I believe, right? It's quite a joy to work with this, and would I use it in production? Probably no. I gotta be honest there. For no particular reason. It's just that it's quite young of a project. I believe it's got a great direction. Full disclaimer: I'm not involved in this in any way. So I just wanted to show you guys what this looks like, and that you can combine Rust and Python with a very low overhead, very low boilerplate kind of fashion. Yeah, but apart from that, thank you for your attention. And
thank you, Sven, for the talk. If anyone has any questions, just line up at the mic on the side, and please speak up close to it because the volume is a bit low.
Hello. Does Cargo generate Python files when you compile these Rust code, or how do I tell Python that there is actually a compiled Rust module that I can use in Python? Or is there something that I have to add to setup.py?
I don't quite get it, to be honest.
So if you compile the Rust code with Cargo, you get some binaries?
Yes, you get an SO, like you would get if you compile the C extension module, for instance. And Python can directly import SOs.
Yeah. But you have to add it to setup.py so that it gets packaged with your Python.
Yes, you do.
Thank you.
Hi, thanks for the talk. Does Pio03 give any kind of direct interoperability with NumPy and its format of arrays?
No, I don't believe so. But you could add traits to do this. and you can do your own kind of exchange functionality during in the like where you had this PyFN thing. You can declare there and probably find an efficient way to do this. If in case that I suppose NumPy exposes a C aligned array, and if you have that, you can very efficiently do that.
Thank you.
Could you go back to the slide where Rust is calling Python?
Absolutely. Like, sorry? No? Right, there we go. Yes?
So on the third line from the end, you've got sys.get version.
Right.
And in Python, the dot... Never mind, I've just figured it out. Sorry, I was trying to figure out how Python knew the sys module had a .get method. But that's not a method in the sys module, that's ignore me. Sorry.
No worries.
Any more questions?
I'll ask one question. I mean, what would you recommend as like a path for learning Rust?
A path for what?
What resources have you found useful in learning Rust?
Oh, and learning Rust. To be honest, there's this Rust book. It's just called that Rust book. Actually, version 2.0, yes. And it's really quite good. It's written by some core members of the Rust team. And to be honest, this way you learn a lot of Rust. There's also the Rust cookbook and also Rust by example, which are all great resources. And you can actually just kind of click the code and it will compile on some server and run on your browser. And this is a quite nice way to explore that. But you can also quite easily just install it on and basically every system it will work.
One more question.
Hey.
Thanks for the talk. So if you want to do SIMD instructions, is it like, does Rust provide like some blocks where you put assembly in, or do you use something like intrinsics in C?
No, you don't use. You can use intrinsics, but we don't do that. So as I said, like if you have a look at this syntax here, where you have basically into par iter, right? This will give you a parallel iterator over like that will just kind of do the parallelization for you. And there's a library called faster, and it will do the same thing, but using SIMD instructions. So essentially, you don't even see that it's a SIMD-based backend. It will just do this for you. In fact, we could have combined that, but to be honest, I thought it would get quite confusing, right? Because you have two parallelization things going on. But basically, you have three levels. You have the architecture-based intrinsics, which you can use directly if you're feeling like that, right? But then you can have also the standard SIMD, which is just a tiny bit above that, which kind of abstracts everything away from you. And then you have crates, which again build on top of that and give you very nice abstractions on top of that, which will also do like runtime detection. And then you have like ways to kind of fall back from AVX2 to AVX if you don't have that hardware. So it depends on how you want to do this, but like everything is there.
Thank you.
Right.
Is there a way to automate the generation for deployment? I mean, you're going live into a Linux system, or you are working in your macOS environment. You need to compile by yourself, or you can somehow automate it in your setup.py.
You mean compiling of the Rust?
Instead of including in the bundle all the SEO files, how do you go to production with Rust plus Python code? We'll just.
I mean, what you can use Milksnack, for instance. You could use that in order to easily package that. But to be honest, I just have my setup Py, and it will put the binary into there, and it will just work.
Okay, so you are there at the binary. I mean, if there's a way to automatically compile in the moment that you first run the server.
Oh, I see. So you want to basically compile the Rust code without pre-compiling that. So you want to kind of compile in production.
Yeah.
Ooh, I mean, I mean, I suppose you could do that. There's nothing stopping you from that. I would not recommend that because of the performance characteristic that might be a bit hazy, especially if you have a lot of Rust code to compile, and especially because like the cargo instruction or the cargo build might download some other crates, which might be a security problem, right? Or you might have like proxy issues. So I would certainly not recommend that, but there's nothing stopping you from like having a Rust binary which does that.
Okay, it's about the bundle generation and everything. Yeah.
Yeah, I would certainly pre-generate that for production at least.
Thank you.
Right.
That's it. So thank you again for the very nice talk.